So today we're going to look at that question you were all asking yesterday. How do you know whether how do you figure out what the slowest step is? How do you figure all that out? And the answer is if we wanted to actually figure out all the steps of a reaction, which one was the slowest, there would be a lot of experimentation you'd have to do. But we can figure out the rate law. We can figure out at least what the slowest step involves pretty quickly. Because what you can do is you can just design an experiment. Let's say we have a nice simple reaction. I want to start with this one because in this case, how many reactants do we have?
3.
How many reactants do we have?
1.
Yeah, we have 3 species in the reaction, but only one of them is a reactant. So, obviously, the possibilities, don't write this. Look at me, pencils down, put them down, you. The possibility would be if this all happened just at once, you would just say the reaction is just going to be some constant K times the concentration of A, right? Maybe 2 A's have to bump into each other for this to happen, in which case the rate would be some constant A times A squared. Maybe 3 of them have to bump into each other, which would mean A cubed, right? Or maybe it's even weirder than that. We're going to look at the first example. You could get what's called a zero-order reaction. And this is where, if you look here, by the way, this is what would happen if you have an enzyme, for example. Do you remember from biology class what an enzyme is? Does anyone remember? If you don't, that's okay. An enzyme would be a little like protein whose job is to make the reaction happen, literally like a little piece of cellular machinery. And if you have a machine, it may actually be the case that even if you have 6 million sugar molecules, if you only have one machine that can only take 1 sugar molecule at a time, does how many sugar molecules you have matter? No, right? You could triple how much sugar you have, but if that machine can only go at its speed, then nothing should change the rate. Does that make sense? So in this case, you'll actually see this sometimes. How do we test to know what the rate is? Well, we say, okay, we're going to do the reaction multiple times. So we're going to repeat the reaction with different concentrations of A. And we're going to compare the rate of each. Does that make sense? So if you look here, the first time we ran this reaction, we set the initial concentration of A, and I should put the word initial here because that's what we're starting off with. Obviously, that's going to change as we go along, right? We set the initial concentration of A to 0.1 molar, and how fast did the reaction go? We used up 0.15 moles per liter per minute, right? In other words, molar per minute. Okay. Then we did the experiment is such that we said, okay, now to see how the concentration of A affects this, let's try doubling the concentration of A. So we ran the experiment again, but now what did we set the concentration of A to? Not 0.1, but 0.2. We doubled it. And we watched the rate, and in this case, what did we notice happened? No change. And then, just to double check this, we ran it again. This time we made the concentration 3 times as big. And what did we observe?
4 times.
Oh, sorry. Thank you. And what did we observe?
No change.
No change. So this, what we call a zero-order reaction, is a reaction where it doesn't depend on concentration. These are pretty rare. Like I said, they're pretty much limited to things that are mediated by something else, like enzyme-mediated reactions, or sometimes maybe a reaction that has to happen like physically in a spot, like those reactions that have to happen in what we call a nucleation site, or if you have a perfectly flat surface, but there's one little imperfection, that's where the reaction's happening. But here you're talking about some sort of reaction that is mediated by something such that it doesn't depend on concentration. And in that case, we could say the rate of this reaction is equal to some constant K, and then does the concentration of A matter? Not at all. In fact, we would have to put that A to the exponent. Now, we'd never actually write it that way. We'd just say that the rate is constant. In this case, what is the constant in all the setups here? 0.15 molar per minute. Does that make sense? And this constant would depend on things like temperature, pressure, the nature of the reaction, enzymes and catalysts. So all of those things will still affect the rate of a reaction, but if you keep those things constant, we can build all of them into a constant K. What we're saying here is, in a reaction like this, in a zero-order reaction, the concentration of your compound has no effect. Does that feel okay? You won't come across a lot of zero-order reactions. You'll come across them in biology, where enzymes limit things. In the kind of chemistry we tend to do in a high school lab like physical chemistry, you're not going to come across a lot of zero-order reactions. But I want you to be aware of their existence. Most of the time, if you change the concentration of a reaction, the rate is also going to change, right? And in this example, a first-order reaction, we say the relationship is linear. If you've taken functions and advanced functions, you should be comfortable with the idea of first order, second order, right? In a first order reaction, the relationship is linear, which means this time we run the experiment, and at 0.1 molar concentration of A, the reaction goes at 0.15 molar per minute. But if we double that, what happens now to the rate? And if you can't eyeball that, what could you do? You could always divide them, right? 0.30 divided by 0.15 is 2. Therefore, when we doubled it, it doubled. And then when we multiplied it by 4, what happened here? It multiplied by 4 as well. In other words, however you change A, that's how the rate changes. Does that make sense? Well, that is a linear relationship. So how would we write that? We would say rate is equal to K times the concentration of A, and no exponent needed, right? This means that in this case, the slowest step just involves A bumping into something, the catalyst, the side of the wall, just whatever. But the more A you have, the more it's going to go. This would be a classic decomposition reaction where it just has to destroy itself. Does that make sense? It doesn't actually have to bump into anything else. It's just all by itself. Can you kind of picture that? And obviously, if all it has to do is heat up enough that it flies apart, the more you have, the more it's going to fly apart every second. And the less you have, the less it's going to fly apart every second. So it's a nice linear reaction. Does that make sense? The way you would interpret this is that it doesn't have to collide with any other molecule. It just kind of falls apart at a certain rate. It decomposes at a certain rate. Linear relationship. So if you double how much A you have, then you're going to double how much A is falling apart. If you triple how much A you have, you're going to triple how much A is falling apart. Does that kind of feel okay? And sorry? These are different reactions. I'm using A, B, and C are not real compounds here. We're talking about examples of types of reactions. So the real thing here might be, this one might be glucose breaking down into carbon dioxide and water. That's going to be zero order rated because you're saturating an enzyme. Okay? And then this one here might be, it might be water naturally decomposing into hydrogen and oxygen. And that doesn't involve a collision. It literally just involves them having enough energy to split apart. And that naturally happens at a certain rate. And that means that if you have twice as much water, it's going to fall apart twice as often. And if you have 10 times as much water, it's going to fall apart 10 times as often. It's just a linear relationship. Did that make sense? Did that answer your question? All right. Now we might have another example here where for something to break apart, it actually has to bash into itself. So the actual step, all right, that means that the step here, this is actually, since that is what you would get from this, it actually just means that this is its own slowest step. There isn't any kind of other step to see. Whereas this one here, if we look, first let's see what happens. We set up the same experiment. We run the experiment, we see how fast it goes. Does that make sense? And then, like last time, we double the concentration of A to see what happens. And when we double the concentration of A, this doesn't double. 0.5 doubled would be what? 0.30, but that's not what we get here. And if you can't eyeball this, do the math. What's 0.60 divided by 0.15? Use your calculator. A lot of people use their calculator, but okay, you're right, it's 4. Which means doubling isn't doubling. Doubling is making it go up by 4 times. What's the relationship here? Well, we could try it another way. What did we multiply the concentration by here?
4.
We multiplied the concentration by 4. Now let's see what happens here. Oh my God, that's way bigger. What is 2.4 divided by 0.15? No. Do it on your calculator. We're just guessing here. Do it on your calculator. Get a calculator. You're getting a calculator today, I promise. So get your calculator. Do that. Don't guess at me. Well, it's not. It is, but you were just guessing.
No, I know.
Yeah. You don't fool me. You don't fool me. Yeah, very good. So, what's going on here? Well, the relationship is 2 to what mathematical operation is 4, and 4 to that same mathematical operation is 16. Sorry? Squaring, right? That's a squared relationship. 2 squared is 4. 4 squared is 16. So the relationship here is that we take the rate, it's going to be some constant k, but then whatever we do to the concentration of A, that effect is going to get squared. Does that make sense? This relationship is quadratic. You don't need to know this, but if you want to understand why that might be, because if you look at this, what we learned yesterday says that this should just be rate equals k times concentration of A, right? But that means this must actually happen in steps. Interpretation? The interpretation is there's a middle step. And you can actually tell me what that middle step is. At least one of the middle steps. We don't know how many steps there are. This could be a 52-step reaction. But one of the steps has to be what? One of the steps has to be A bumping into A and doing something. Does that make sense? Because the rate of that would be rate equals k times the concentration of A squared. Does that make sense? That we can make a physical interpretation from what we observe with the rate. Thank you so much. Does that kind of feel semi-logical? Oh, interesting. But this is the overall rate law here. How's that working for us? Now, do you see how we're getting the data from the experiment? In a real lab, you'd actually have to do this experiment. You would have to set it up, measure out the concentration of A, start the reaction, time how fast it goes. Then you'd have to do it again, only this time double the concentration of A, see how fast it goes. Do it again, double it again, see how fast it goes. And when you're seeing that relationship, that will let you say, okay, this is what's changing here. Yeah?
So you know how for the heat of the reaction we had standard values for every reaction or every molecule? Is it the same for rate of reaction?
If you're wondering, can you look up the K value for a reaction? Yes. And just remember that K value is going to be at a particular temperature, just like your enthalpies of formation, at a particular temperature, at a particular pressure, for that specific reaction, in the presence of specific enzymes and catalysts. And if you change any of those things, then the K value will change. But yes, there's absolutely tables of K values, just like there were tables of standard enthalpies of formation. This is in the handout folder, I believe. Is that where we put the extras? Yeah.
Right at the front.
Perfecto. So we are gathering this data empirically. What's that mean to gather the data empirically? What's empirical data? Sorry? Yeah, what's empirical data? What's that mean? It means that we are gathering it by observation. We're actually doing the experiment. Sometimes we'll also use the term experimental data. To figure out the rate relationship, you have to do an experiment because it can fool you. to look at this, you would assume that it would be first order, right? You would assume that it's just going to be rate equals the concentration of K times the concentration of A. But this tells us that there must be a slow step in the middle where A has to bump into A, because what actually happens is that it is second order. We've got this quadratic relationship. So unless you know all the steps of a reaction, you have to do and know the speed of all those steps, you have to do an experiment to figure out the actual relationship. Does that feel kind of okay? Now, this might seem bad enough, but keep in mind that this only had one reactant. But of course, does every reaction only have one reactant? No, in fact, most tend to have at least two, right? So now, for reactants with only one reactant, they follow the idea that we're going to have rate equals some constant K times the concentration of that to some exponent, right? And this will depend on the order. And it must be found empirically. That isn't spelled right. I'm just going to say experimentally. Then I don't have to embarrass myself by spelling that incorrectly in front of you all, though I countermanded that by telling you why I was changing it. And again, remember, this is constant so long as temp, pressure, catalysts, other conditions are all constant. So as soon as you change any one of those, the K value is going to change. Does that make sense? So when we do this rate law, we're trying to lock in on the effect of the concentration of your reactant, but to do that, we have to lock all the other things in place. Okay, can we move on to two reactants? Okay. Does everyone have this down, or do you want a minute? Yeah, take a minute.
So if it's the same molecule, like if it's a diamond molecule, like A2.
That's a single species. Yep. What do you want? Do you want to grab a laptop so you can put it directly in front of you? You can grab one from my office. Did you answer your own question? So I want you to know I was getting ready to answer you, and then you just kind of petered off and sound like you know what you're doing. What? Probably not. When it comes to visual spatial stuff, I'm like a real grade A moron, let me tell you. All right, so, and then there were two. When there are two reactants, you need to determine the order of each reactant individually. Does that make sense? And again, look at me. If we knew that it was a one-step reaction, we could just use the coefficients, right? If it were one step, we could just say we know that the exponent will be the coefficients. But most reactions, especially of bigger molecules, as it turns out, do not happen in one step. And so we have to experimentally look and see what goes on here. So you might have two reactants, A plus B, and in this case, I want to stretch out, it doesn't matter what the coefficients are. Again, if it all happened in one step, you could just use the coefficients to give you the exponents. but we can't assume that. So it actually, for the purpose of what we're doing here, it is likely that if something has a higher coefficient, it likely will be one of your things where the concentration matters, but there's no guarantee of that. You have to do it experimentally. So if you look here, we know that the rate is going to, generally speaking, be some constant k times the concentration of A to some exponent times the concentration of B to some exponent. But the thing to know is that both of these must be found experimentally. Assuming you don't know it to be a one-step equation. Again, if it's a one-step equation, they will just be the coefficients. But it probably isn't a one-step equation. So, with that in mind, let's look at this reaction, where some number of A plus some number of B gives us C. What we can do is we can set the whole equation up, just like we always do, and the first time around, we lock in both of the concentration of A and B, and we get a baseline rate. Does that make sense? Now, do we want to change both of these at the same time? No, we want to change just one of them. So look here, when we double just A, but then we leave B alone, right? No change. What happens to the rate of the reaction? No change. What does that tell us? Sorry? Good. So we would say the reaction is what order relative to A? Yeah, this reaction is 0 order relative to A. So we can say, therefore, the rate will be K times the concentration of A, don't need it, times the concentration of B to some question mark, right? That's a 0 exponent. We can conclude that for this particular reaction, the concentration of A isn't going to change anything, right? Because when we doubled it, what happened to the rate of the reaction? Nothing. Yeah, it stayed the same. So now let's look at the other case. Here, we keep A the same, no change to A, right? But what do we do with B here? We doubled it. So this is a well-designed experiment. In the first step in the first two things, we saw what happened when we changed the concentration of A. Now with the third trial, we're seeing what happens when we change the concentration of B. And what happens? You can probably eyeball this one. But if you couldn't, what do you do with the two numbers to know what happened? You divide them. So you do 0.30 divided by 0.15. And as it happens, that's going to give us 2. Which means when we double the concentration of B, what happens to the rate? It doubles. Therefore, what can we conclude? The reaction is what order relative to B? Is first order. It's linear, right? And so therefore, we can say, what will the rate law be? The rate is K times A to the exponent 0, in other words, it doesn't matter, times the concentration of B to the exponent 1. And how would we write that cleanly? We would say the rate law for this is rate is going to be some constant K times concentration of B. And do we need any exponents at all? None.
So for the reaction A, would the rate be A only?
Yeah, and if you look here, I just crossed it off. And B we didn't know yet. Do you know what I mean? In the end, we're only actually interested in writing the overall one. This is just me kind of going through my thought process. Does that make sense? I'm just kind of showing that as I'm thinking about this, I'm saying, okay, I need to know, like I kind of start off by saying, okay, rate is going to be equal to K times A's concentration to some exponent times B's concentration to some exponent. And now I'm working out what those numbers are. So the first thing I do is I check, see what A does, and I say, oh, A doesn't matter. Don't need to worry about it. Then, when I go through and look at the second one, I'm saying, okay, we already knew A doesn't matter, and now I'm figuring out that since it's first order, B matters to the exponent 1. Then obviously I'm going to write it nice and cleanly, where I'm not going to bother writing A to the exponent 0, and I'm not going to bother putting in an exponent of 1 on something. Did that answer your question? It was a good question. How's that feel? Okay. I feel like I'm like, we're not getting to the chat point where we're like doing this yet, but I do want you to follow along with me just because it's important to make sure we can do this. So in this case, we'll do that same thing where we say like, okay, the rate is going to be some constant k times the concentration of A to some exponent times the concentration of B to some exponent. And the question is like, okay, what are these numbers, right? Does that make sense? And so we could say, okay, let's look at the concentration of A first. So we set the reaction up, and then we change the concentration of A. And what did we change it by here? Yeah, and listen, if you're designing this experiment well, that's what you're going to do. You're going to make your life easy. Just double the concentration. Could you pick random numbers there? Yeah. Are you going to get some textbook questions that have annoying, ugly, stupid numbers? Yeah, because whatever, that's part of the game. But if you're actually doing this experiment, why would you make your life hard? Just double one, leave the other alone, and see what the change is. In this case, when we double A and leave B alone, what do we get? Double the rate of the reaction. Which means what can we conclude? We can say relative to A, it is zero order, first order, second order? First order. Which means that that exponent is a 1. Does that make sense? Then we could just do the same thing for the second. Now we're leaving A alone, so we're ignoring it. But what are we doing to B? Doubling it. And when we do that, what happens to the rate? It doubles, right? And so if doubling the concentration of B doubles the rate, then relative to B, what is it? Yeah, it's also what order? First order. Good. And so that means that this is a 1 as well. And so then when we actually go to write the rate law nicely, we just say the rate is some constant K, as long as temperature, pressure, reaction conditions, catalyst, all that jazz is there, times concentration of A. Do I need to put an exponent 1 there? Could I? Would I be wrong? No, but you'd be clumsy. Trush would laugh at you. He'd be like, they're so silly. I wouldn't be able to argue. So that would be our rate law. Does that kind of feel okay? I want you guys to do example 6. In this case, one of them is first order, one of them is second order. I want you to figure out which is which and you to write me the rate law. And again, I kind of like to, in my head, I don't actually write it on the page normally, but in my head I'm thinking this, which is we've got these two exponents and we just need to figure out what they are. All right, so take a minute, do that.
Mr. Lando?
Yeah.
Someone just got this calculator really weird. Like, so it's always going like E to the something.
Sure, so just press the reset on the back. You know this little... Yeah, and it's got like a, you need a pencil to... You usually have to like hold it for a few seconds. Any Billy Bragg friends in the house? Thinking back now. That's a weird key. I suppose you would just stayed in your views. What was it all for? That's a horrible key. Was it for the weather or the battle of Agincourt? And the fun we all hoped would last, like a train they have come by so fast. And though we stood together on the edge of the platform, we were not moved by them. Thanks all the same. Ooh, I hate that key. Wow. No, thank you. I'm used to playing that on like a on a normal like what is it, a soprano ukulele? Is that the normal one? Because this is a tenor ukulele. I had my banjo now, I'd... I'm faster than a beginner, but okay. There's a guy named Earl Scruggs, and he literally invented the most common kind of banjo picking called Scruggs picking. So this guy is like a godfather, and I think he's dead now, but I saw him play at the Newport Folk Festival in 2010, and dude was like, I want to say 91, he was old. And his band was all like his family, and at first it seemed like elder abuse. Like the band comes up and starts playing, and then these two guys walk dad out, and dad looks like a skeleton being propped up by these two guys, and you're like, I feel gross about this, right? And they strap a banjo on him, and he's just sitting there kind of like this, and the band is playing, and they're pretty good, and this guy's every once in a while going like, and you're like, this is cruel. Like, and then about 30 seconds in, they're doing this song, and all of a sudden they go, all right, dad, go. And guy just starts like I've never seen anything like it. And the whole audience was like, like he just friggin', and like his body didn't move an inch, like and he just kind of looked ahead like this, and just, it was wild. It was absolutely wild. It was like breathtaking. And then dude did like an hour set, like, and then at the end they walked him on out. But it was crazy. I was like, wow, like man, if my fingers can do that at 92 years of age, I will be doing all right. I mean, they won't be able to because they can't do it now. So why would I be more dexterous at 92? But I was like, that was when I was like, all right, I got to learn to play the banjo. Because it was, sorry? I don't know the name of the band, but his name is Earl Scruggs. And he's like the guy who, and I mean, there's a million fast banjo players out there, obviously. But he's like kind of the godfather of it. And boy, it was the first time I'd seen like a serious banjo player just like go for it in my life. And holy crow, like, man knew what he was doing. All right, have we got this? All right, talk to me. What'd you do? Mm-hmm. Okay. Okay, so you did 0.60 divided by 0.15, and you got what? Okay, now, can we be sure that that is all about A? I think we can, but how can we be sure that that's all about A? What did they do to B here? Yeah, they did nothing, right? Okay, so obviously doubling A is causing a 4 times change in B. So what did you conclude from that? Or in the rate, rather. So what did you conclude from that? Okay, so it's second order relative to the concentration of A, which means we can put the exponent of 2 here. Cool. Okay, somebody else. What do we do after that?
So you can see in the third step.
Like this row here?
Leave A the same and double B.
Okay, so no change there, but they double B.
And the concentration doubles.
Not the concentration.
Or not
the rate. Good. And so if doubling the concentration doubles the rate, that means it's not second order, it's not zero order, it is first order. That's a linear relationship. Good. So it's first order relative to the concentration of B. And so if we were writing this rate law nicely, how would we write it? Yeah, rate equals some constant K. Yep. Very good. Beautiful. Look at you guys. Look at you guys. Note that what we call the overall reaction rate is just the sum of the individual reaction rates, right? So in this case, we'd say its overall order is 3. Good. And that means that in the slowest step, 3 things need to collide. Does that make sense? Like, what this is telling you is that in the slowest step, 3 things collide. That's the physical interpretation of that data. And specifically, we know it has to collide. 2 A's and a B collide in the slowest step of this, right? Which means that even though this reaction only involves 1 A colliding with 1 B in net, there's a stage where 2 A's and a B actually have to pump into each other. Does that kind of fit? Kind of weird to think about. What's the overall order here? Yeah. And I'm not going to write it every time, but that means that in the slowest step, 2 things have to collide. Specifically, what has to collide? A and B have to collide. What is the slowest, what's the overall order here? Yeah, the overall order is 1, which means that here nothing has to collide. The slowest step just involves B doing something. Giving up an electron, taking an electron, decomposing, whatever, changing shape. The slowest step here doesn't depend on a collision. It doesn't depend on anything else. It's just B doing something. Does that semi feel okay? All right. So the last thing is, can we figure out what K is? Right? Like we keep saying some constant K, but there's no, this is useless to us if we don't know what K is, right? And you ask, can you just look it up? And for some reactions you can. You can look up rate constants for reactions under very specific conditions. And if you're doing industrial work, you could look that up, like if you're doing industrial chemistry. But of course, where did they get those numbers? They did experiments. And actually, exactly the kind of experiment we see here is we already have all the information we need. So let's go to the next one. And in this case, we're going to determine the rate law, but then we're also going to determine the value of K. Now this one kind of sucks. This would be exactly how not to do this, right? But I wanted to give you one where you just see, sometimes in the textbook, sometimes whatever, they don't do a nice job with it. You've got to find the combinations where things change nicely so you can do a bit of easy work. Does that make sense? So if you look here, if we treat this as our baseline, is there any situation where we've only changed one thing? And that doesn't have to be the one you treat as your baseline, might I add. But if we treat that one as our baseline, what could we look at that's only changing one thing? Reaction. Okay, in reaction 4, we've changed this, right? But we've left this the same, right? No change there. What did we multiply this by? Okay, that's a bit more annoying to work with, but that's okay. Then our question would be, what did this change by? And I'm going to put a little asterisk here because there's not a lot of room. How could we figure that out? Divide. So I could do 0.01406 divided by, what's the other one? 0.00156. And what do we get? 9.01. In other words, 9. When we triple the concentration of Xe, the rate gets increased by 9 times. What could we conclude from that? Is it first order? No, because if it were first order, tripling would result in tripling. Is it zero order? No, because then tripling would result in no change. So in this case, it means that this is, sorry? Is it third order? That would mean cubing. Is 3 cubed 9? No. What order is it? Second order, because second order would mean to the exponent of 2. And what's 3 to the exponent 2? 9. Since 3 to the exponent question mark equals 9, well, 3 to the exponent 2 equals 9. Therefore, second order. Does that make sense? So if we start filling in our little rate law where we'd say, well, rate is going to be some constant K times the concentration of Xe to some exponent times the concentration of F2 to some exponent. Well, we just found out that our exponent for Xe is 2. It's second order for that. Does that make sense? Because if doubling is 4 times as big and tripling is 9 times as big and 10 times in the concentration makes it go 100 times faster, that's second order. That means we're squaring that effect. All right, what's the other one we need to check up on? You want to go with the fifth? Okay. I don't think the fifth is...
Yep.
I mean, you can, but that's changing... Oh, it's just changing the F, isn't it?
Yeah.
Oh, never mind. I'm good. I'm blind. So that's no change here. That's good. And what are we multiplying by here? We're multiplying by 4. And then here, let's do the same thing. Maybe you can do that in your head. I can't do that in my head. So we would say we do what to figure this out? Divide. So we do 0.00625 divided by 0.00156. And we would get what? That's going to be 4 pretty nicely, right? If we round it to 4. And so making it 4 times bigger makes it go 4 times faster. What order is that? First order. And that means our rate law is the rate equals the concentration, some constant K times the concentration of Xe to the exponent 2 times the concentration of F2 to no exponent. But now, let's find K. And how the heck do we do that, mathletes? Yeah, if you look at this, it's an equation, and how many variables does it have? Rate, K, it's actually a constant, so we call that a parameter, but you get the idea. Rate, K, Xe, and F2. An equation with 4 values, how many of them do we have to know if we can solve for one of them? You have to know 3 of the 4. Do we know 3 of the 4? Yeah, and here's the deal. In theory, look at me. In theory, it should make no difference which of these sets of data you use as long as you use them. So let's do this here. Ready? I want you to do this math using experiment 1. I want you to do it using experiment 2. 3, Eng 4, Novak 5, Mila back to 1, Samuel back to 2. I will do it for experiment 3. It doesn't matter which one you do. I'm going to say, let's use the data from experiment 3. But we should all get roughly the same answer. Because it's real experimental data, should it be exactly perfect? No, but they should be really close. So I'm going to use experiment 3 above. And in experiment 3 above, for me, the concentration of Xe is 0.75. The concentration of F2 is 0.25, and the rate is 0.0032. And what are the units on those? Molar, molar, and molar per second. Molar, molar, and molar per second. And now I'm just going to solve this. And I want you to do the same. What are we solving it for? Team, what are we solving it for? K. So I'm going to do mine, you do yours. No cheating, unless you need to. Don't mind me, just doing a little bit of algebra, because of course we're all algebra pros. You cannot do advanced science without having decent algebra chops. Uh, 0.0032 molar per second divided by 0.75 molar squared. All right. Zero point 0032 divided by, open a bracket, 0.75 squared times 0.25, close that bracket. Let's talk units.
No. 0. That's done. Never mind.
How'd we do? Do we agree? Did you get yours done? So we can see that's experimental error, right? Which is fine. We're agreeing with each other. If you were doing this for real, you would do them all and take the average, right? Everyone should get somewhere around 0.024. Some will be a little lower, some will be a little higher. That's the value I plugged into this experiment before I then said, make little random errors, which I had the thing do on purpose. I set up in Excel. I just wanted to kind of model, something resembling. What did you get?
0.02496.
So 2.5.
Yeah.
Right? Because how many sig figs do we have here, of course?
Yeah.
2 sig figs, right? Okay, and then be careful about units. Units matter. And the units will be different every time. You just have to track them. Look here. In the top, we had molar per second. Are there seconds anywhere else? Then the per second is going to live. If you want to write it as per second, you can go nuts, but I chose instead to write it as s to the negative 1, right? That's sort of the more accepted thing when you don't have a unit on the top. And then look here, I have 1 molar on the top, right? That's going to cancel with one of the molars on the bottom, in this case, but I still have molar squared on the bottom, which again we will typically write as molar to the negative 2. That is just a way of saying molar squared on the bottom of the fraction, seconds on the bottom of the fraction. If you preferred to write that as 0.023 over second molar squared, you could do that, but it's clumsy. This is kind of the way you'll typically see units written like that. I want the units to be included. Does that make sense? And you can't assume they will be different depending on what the order of the reaction is. Does that make sense? Look at me. Look at me. They will be different depending on the order of the reaction. Okay, so then the last step would be let's properly write the rate law. We can now say the rate of this reaction will be 0.023 seconds to the negative 1 molar to the negative 2 times the concentration of Xe squared times the concentration of F2. That is the rate law for this reaction under these conditions. And now if I wanted to, I could say, if I set the concentration of Xe at 0.15 and the concentration of Fe at 0.2, what would the rate be? And you can just work it out. Does that make sense? Yeah.
I'm sorry, I didn't understand your explanation for the
Okay, so negative exponents, if you recall, do you remember that a to the negative 1 is just 1 over a, and a to the negative 2 is just 1 over a squared? Do you remember those exponent laws from math? So all we're saying here is if you look at the way the units work out in this, they all actually end up being on the bottom of the fraction, right? Seconds this was molar per second. So seconds is at the bottom of the fraction. And then this molar is going to cancel with that molar, which means that this molar squared is also at the bottom of a fraction. How do you write a unit when it's got a bottom of the fraction but no top? So you could write this as 0.023 per second molar squared, but there'd be nothing up here. Does that make sense? I guess you could write a 1 up there, and that would be mathematically correct, but it would look kind of clumsy. So the way we write it is we just say these units are on the bottom of the fraction. There's a seconds on the bottom, so we put negative 1, and that means that's per second. And then molar squared with the negative exponent means per second per molar squared. So it's just telling you those are on the bottom of the fraction. Did that answer your question? Cool. That is a tricky thing. So again, once we have this equation, then you can get the reaction to go whatever speed you want by setting the concentrations. And if you set the concentrations, you can figure out what the speed of the reaction will be. You now know the mathematical equation to determine the rate of this particular reaction under those particular conditions. Now keep in mind, if you change the temperature, this breaks because the K will change. If you change the pressure, this breaks because the K will change. If you change how much catalyst is present, this breaks because the K will change. So this is still only valuable under certain conditions, but it's still a very useful thing. Does that make sense? How does that feel? And remember that if this all happened at once, if it was a one-step reaction, you could just get that straight from the reaction. But because these can take multiple steps, in this case, what is happening at the slowest step of this reaction? Well, two xenons, or two things that were derived from xenon, are bumping into one fluorine, or one thing that was derived from fluorine, and that's the slowest step. Does that make sense? That's really what we're describing here. Even though the overall reaction involves one xenon bumping into three fluorines, at the slowest step of this reaction, two xenons or xenon derivatives are bumping into one fluorine or fluorine derivative, and that's the slowest step of the reaction. Any questions about that? That cool? Yeah.
When you say fluorine derivative,
It could be, it's possible that like maybe in step one, fluorine first has to bump into yttrium, which will never happen, by the way, and form a fluorine yttrium thing. That might be a fast step, so we don't have to worry about that. And then it could be that here, two xenons have to bump into that fluorine yttrium and form Xe2FY, and that's the slow step. The fact is that what would actually depend on then is the concentration of Fy, but that doesn't really matter. That's a derivative of the fluorine. So in the slowest step, it's two xenons bumping into something that came from fluorine. Does that make sense? And again, you don't need to know that. I think it's just helpful to understand where this math comes from, which is it doesn't just come out of the blue. It's not just random. It's not made up. It has to do with the physical geometry of things bumping into each other. If that makes it more confusing for you, you can ignore that completely and just follow the steps. But I found that most people find it helpful to be like, well, y squared, y cubed? It's really describing things bumping into each other and the probability of that happening. Did that answer your question at all?
Yeah.
Did it actually, or are you just shutting me up? Oh, it's a miracle. Any other questions? All right. There's some homework and practice on here. This is a key concept, key skill. So let's make, yeah. Can I do what? I can, yeah.
So you see how 1 percentage for -4 is changed to -3? It's not like that.
That is 20 times bigger, right? Because that change in exponent. Yeah, guys, shh. I would definitely be doing dividing on my calculator with these unless you're pretty intuitive. Like if you look at this, at first glance, that might look like no change. But actually, what's the change here? What are we changing that by? If it goes 10 to the -4 to 10 to the -3, that's getting 10 times bigger, right? Which means that this change is actually getting 20 times bigger. Or if you prefer, you could look at this one and say that's just getting 2 times bigger. Does that make sense? So when it has scientific notation, you got to watch out. It's easy to make a mistake. But we can do it. When in doubt, just divide, right? If you're not sure, just do 1 times 10 to the -3, divide by 1 times 10 to the -4. And when you get that, it'll say, oh yeah, that's 10 times bigger. Yep. Sorry?
So when I divide 0.15 by 0.10, it's 1.5.
I gotta be honest, you just said a lot of numbers at me. Oh, sure, well, that's fine. So then if it's a first order, the rate should also change by 1.5, right? If it's second order, it should change by 1.5 squared, whatever the hell that is, which you can do in your calculator, right? What's 1/2 of 1/2? 2.25, right? Check that. What's 1.5 squared? Should be 2.25.
1.5 is 2.25. But you know how when you double it, it doubles or
Yeah.
it multiplies by 4?
Yeah.
I'm going to do it with times 20 and 1.
Good answer. So if it's first order, guys, that is a good question. So look here, I actually really like this question because this question sucks and they do bad multiplying, right? So let's say that we change the concentration of A and we increase it by 10 times. If it's first order, what will the rate then change by?
10.
Yeah, it'll change by 10. It's linear, right? On the other hand, if it's second order, and we change the concentration of A by 10, then we would expect the rate to change by how much? By second order. Second order means we do what to this number? So it should change by 100, right? On the other hand, if it's second order, if we multiplied this by 6, that's annoying, we would expect the rate to go up by how much? 36. Does that make sense? You just square it. And if it's third order, which you're not going to see a lot of, in fact, I'm not even going to bother, you're never going to see third order, but it would be 1,000, right? And keep in mind, you might get something really ugly. What if they change the concentration of A by, I don't know, 1.5? Then we'd expect the rate to get multiplied by 2.25, because that's 1.5 squared, right? Is that okay? Does that feel not too bad? Just bad enough? Just bad enough. All right. This is something I'm going to put on my gravestone.